Hello everybody, we're team A23 and our topic today is Bayes Theorem. And after watching this video, if you feel that you need any more help with discrete mathematics, make sure to check out www.knoatom.com. So, to start, let's quickly write down what Bayes' theorem actually is, and then we can go on to prove it. So Bayes' theorem is actually very useful when you're considering the probability of one event given another event. So in this case, assuming that the probability of E is not equal to 0, and the probability of F is not equal to 0, we can find that the probability of F, given that event E is true, is, on the numerator we have the probability of E given F, multiplied by the probability of F over the probability of E given F multiplied by the probability of F again, you see that in the numerator, plus the probability of E given not F times the probability of not F. And while this seems like a lot of terms, it actually makes the solving for the probability of F given E quite easy, because generally you have all of the terms on the right side. So it's basically just plugging in that information. So let's go on to actually prove this theorem. So the proof for Bayes' theorem is actually quite simple, and it involves us using our probability rules. So to start off, we know that the probability of E and F, if E and F are just any two events, the intersection between them, are equal to the probability of F given E times the probability of E, which is the same as saying the probability of E given F times the probability of F. And as I said before, we already know this from our basic probability rules. By just doing some simple algebra, dividing both sides by the probability of E, we can get the probability of F given E is equal to the probability of E given F times the probability of F over the probability of E. And quickly, we can notice right away that the numerator here is exactly the same as the numerator that we previously had for Bayes' theorem. So all we have to do is prove the denominator. So proving the denominator is a little bit intuitive, so let me start by writing down a statement. And it is that the probability of E is equal to the probability of E and F plus the probability of E and not F. So now a quick question that you may have upon reading this is, why are we able to say that? And the answer is the cases where of E and F and E and not F span all the possible cases of E. If E and F is true, then obviously those parts of E are spanned. But for all those cases where that is not the case, you must consider when F is not true. And really, from our basic probability rules that we knew before, the probability of E and anything plus the probability of E and not the other thing is obviously equal to the total probability, because F and not F are mutually exclusive. So therefore we can use this information to really write what the final denominator for Bayes' theorem should be, and that is probability of E is equal to the probability of E given F times the probability of F plus the probability of E given not F times the probability of not F. And again, the way that we were able to write this final statement here is that just using the first statement that we had at the top, you know that the probability of E and F is E given F times F, and E and not F is E given not F times not F. And we see that exact formula right at the top of the slide. So we've actually just proved Bayes' theorem. We'll write Bayes' theorem again really quickly to reiterate that. And it's the probability of F given E is equal to, on the numerator, the probability of E given F times the probability of F, which one of those arrows up there points to, And then on the denominator, we have the probability of E given F times the probability of F plus the probability of E given not F times the probability of not F. And this was simply the expression we had for the probability of E right above. So that's the proof, and now we can work on some pretty simple examples. So let's start off with a pretty simple example. So let's say that a class has 60% males and 40% females. Now, of the males, let's say that perhaps 25% are blonde and the other 75% are not blonde. And then for the females, 45% are blonde and 55 are not blonde. So let me write this into the tree real quick. And all right, so let us find the probability that if a student is chosen at random and found to be blonde, what is the probability that the student is a man? So another way of saying this is, what is the probability of a male given blonde? So in order to do this, we can simply use Bayes' theorem, and let's write that out real quick, and that would be the probability of B given M multiplied by the probability of M over the probability of B given M multiplied by the probability of M plus the probability of B given not M, or in this case, since we have only two variables, we can actually erase this not M and write women or females times the probability of a female. And we can only replace not M for female in this case because the probability of M plus the probability of F equals 1. Basically, everybody is either male or female. So let's go to the next step and actually calculate this. So the probability of B given M is 0.25, multiplied by the probability of M, which is 0.6, over, we have 0.25 times 0.6 again, plus 0.45, which is the probability of B given F, times 0.4. And we see that the answer to this is about 0.4545. And yeah, that's basically, it was pretty simple. We were able to just use this formula and quickly obtain an answer. So the next example we look at will be a little bit more complex. So on this slide, let's look at actually a real-life application that is pretty important, and it uses Bayes' theorem. So let's take a situation in which you know of a particularly rare disease, and let's say in general, one person out of every 100,000 people have the disease. So that's 0.00001, and then everybody else does not have the disease. So let's say 0.99999. Now we want to consider the case where these people actually get tested and their tests actually show up as being positive or negative. Generally our tests have gotten pretty good over the years. For people who do have the disease, they will test positive 99% of the time. And they will obviously test negative 1% of the time, and this would be basically a false negative test. And then of the people who do not have the disease, they will have a false positive 0.005% of the time, or 0.5% of the time, and they will have a correct negative test 99.5% of the time. So take a look at this tree. This kind of helps represent the situation. Oftentimes, especially for Bayes' theorem questions that have just two choices in them, it's very useful to draw a tree such as this because it kind of lays everything out for you and makes the next portion much easier. So let's find the probability of a person who tests positive for the disease or the probability that a person who tests positive for the disease actually has the disease. Sorry, that was a little bit confusing, but what I'm trying to say here is the probability that someone has the disease, yes, D, given that they test positive. So there's two situations that we have to take into account for here, and that is those who have the disease and correctly test positive, and those who don't have the disease and still test positive. This case is known as a false positive. So all we have to do here is just use our formula. So this is equal to the probability of P given D times the probability of P, or D, sorry, over the probability of P given D times the probability of D, plus the probability of P given not D times the probability of not D. So we have all of these numbers, and it's just basically plugging it in. We have 0.99 times 0.00001 over 0.99 times 0.00001 again, plus 0.005 times 0.99999. And we actually get that the probability is about 0.002. And essentially, this kind of represents the case of people who do have the disease and therefore get a positive test as a result of this. So that's it for this real-life application. As you can see, Bayes' theorem simplifies this problem tremendously. One last quick thing to note actually about this example, you may think that 0.002 is actually very low. You would think that most of the time the positive tests actually correspond to those who are diseased. But this is not the case, and the main reason is because the 0.99999. The probability that someone does not have the disease is so much larger than the other case that the false positives actually overwhelm the real positives a little bit. So you'll see that most of the time a positive test does not actually indicate that someone has the disease in this case. And that's even with such good statistics for the test. 99% is pretty good. But in the grand scheme of things, when you're dealing with huge numbers, you'll see that a lot of times the very large number or the non-diseased population will kind of overwhelm the other one. So it's something to kind of keep in mind for future probability questions. So that's pretty much everything we have for you today on Bayes' theorem. As you can see, we've really written the formula here quickly, and it's the probability of E given F is equal to the probability of F given E multiplied by the probability of E over the probability of F given E multiplied by the probability of E plus the probability of F given not E times the probability of not E. It sounds like a mouthful. It kind of is a mouthful, but it's actually not that hard to implement, as you've seen during this video. So we hope that you enjoyed and understood it. If you have any more discrete mathematics questions, be sure to check out www.knoatom.com. And thank you very much for listening.